When a lot of people hear about paper folding, they usually think of children's art class or some realistic animals. But paper folding, or origami from Japanese, is actually a powerful mathematical tool. Just like compass and ruler, it can be used for calculation. It can construct all rational numbers, square root and even cube root, or solving equations, quadratic and cubic, are all easy to solve. Folding constructions usually use single folds, meaning every fold is performed after the last fold has been flattened, because the only important thing is the crease. In contrast, multifold means you make another fold before the last one is flattened. Since more information is available on the paper, multifold is more powerful than single fold. But in the following video, I'm only showing single folds because multifold is hard to animate. Some moves that look illegal are actually just simplified double folds. A rational number is just a fraction, so the only hard part is the denominator. As long as we can make 1 over n, just multiply that length m times, and we get m over n. It's pretty easy to make 1 over n if n is 2, 4, 8, 16. With this method, we can turn the easy n over 2 to the r into 2 to the r minus 1 over n. With 2 to the r minus 1 over n, fold the r minus 1 times in half, and there will be only 1 over n, and we are done. Take 1 over 7 as an example. First, we check the table. To make 4 over 7 on TC or BC, we need 7 over 8 on AP or AB. So we fold the paper 3 times horizontally and vertically, making an 8 by 8 grid. Then mark 7 over 8 on both sides. After that, make a fold that lands those two marks together, where that crease intersects the edge is 4 over 7. Finally, fold that length in half twice, and we get 1 over 7. Usually, multiplying that length requires multifold, which is more intuitive, but since I'm not using that, here is a more complex way to multiply length. I put the length on the edge. First, make two perpendicular folds on O and A, the start and end point of the length. Make a 45-degree fold from O by folding O0 to the edge. From the intersection of A0 and L0, make V perpendicular to A0. The last crease is L1, going through the intersection and perpendicular to L0. The point where L1 intersects the edge through O is double the distance from O to A. As we can double distances, we can multiply a distance by any amount we want. For example, to make length 7 times, double the distance 3 times. Now we have 8 times the length. Fold it in half again and again until every section is 1 unit long. Count 7 sections, and it's done. Because it's easy to do this with compass and straight edge, it's also easy with paper folding. Just use the same method. Take square root of 2.3 for example. First, mark 1 unit and 2.3 on the edge of the paper. Fold on point 1 so the crease is perpendicular to the edge. Fold it in half so it bisects the segment. Finally, fold the left segment so the corner lies on the vertical crease. The height where the final point is the square root of 2.3. The way we make cube root of n is to solve the equation x cubed minus n equals 0, which will be discussed after I introduce cubic equation solving. To solve a linear equation in one variable in the form ax equals b, mark 1 and a on the paper edge and b on the other edge. Make a fold between point A and B. The next crease goes through the corner and should be perpendicular to line AB. Finally, fold through point 1 and perpendicular to the last crease. The intersection between the last crease and the edge with B to the corner is B over A, the solution. This is also a way to make rational numbers. The method for solving quadratic equations is less intuitive. To use this method, first make the coefficient of the first term equal to 1. Take x squared plus 2x minus 3 equals 0 for example. First, draw the coordinate system with y equals 1, the line, and 0, 1, the point. After that, draw a point with the x-coordinate being the negative of the second term coefficient of the equation, while the y-coordinate is the third term. That is, negative 2, 3 in this example. Now perform the folding. Make a crease passing through point negative 2, 3 that brings point O, negative 1 onto the line y equals 1. Notice that there are two possible creases, which correspond to the two roots of the equation. To read the root, measure the distance between where the crease passes the x-axis and the origin. Don't forget the sign. Last but not least, we have the cubic equation. The solution involves a method called Lill's method. Lill's method is a visual method of finding the real roots of a univariate polynomial of any degree. That's how Wikipedia describes it. To employ this, start by taking all the coefficients out. For example, with the equation 3x cubed minus 4x squared plus 0x minus 2 equals 0, take out 3, negative 4, 0, and negative 2. Start from the origin. Draw a line going right with the length of the first term 3. Then turn 90 degrees counterclockwise, facing up. Go negative 4 units, which means down 4 units. Turn 90 degrees again, facing left. Go 0 units, which means don't move. Lastly, turn 90 degrees again, facing down. Go negative 2 units, which means up 2 units. It's fine if it overlaps a past line. After drawing out the equation, cast a new line from the origin at the correct angle. This line needs to meet a lot of conditions. The bounce here follows a rule to turn. Wikipedia uses the word reflect to describe it, but to me, bounce makes more sense. The ray needs to go through the last point of the drawing after bouncing polynomial degree minus 1 times. From the starting point, the ray goes. When it goes through the second coefficient straight line, meaning the infinite extension of the segment, it turns 90 degrees and continues. There are two ways to turn 90 degrees, clockwise or counterclockwise. If it hits the segment itself, not just the extension, turn 90 degrees so the ray doesn't go through the line. Otherwise, turn 90 degrees so it goes through the line. I didn't mention clockwise or counterclockwise because it depends. After bouncing from the second coefficient line, it looks for the third line, and so on. Until it bounces at the second to last term line, it should then go through the endpoint. The gray line on screen shows an incorrect bouncing path, just to contrast it with the correct one. So in the end, only the first and last lines are not used as bounce lines. There's three clarifications. First, you can only bounce at a line after you've bounced at the previous one, so you can't bounce at the third coefficient before bouncing at the second coefficient. Second, if the bounce point is at the intersection of two segments, it bounces at the first and immediately bounces at the second. The line turns 0 degrees in the end, so it looks like nothing happened, but it does count as two bounces. The example here shows how the ray goes through such an intersection. Third, if there's a zero coefficient, which is just a point, the extended line still has to follow the direction as if the coefficient were not zero. As for what happens if the ray goes through the zero coefficient, whether it should bounce through or bounce back, I don't know. I think it should be through. If anyone knows the answer, please let me know. I really can't find it online. After the correct ray is formed, the angle between the first segment and the ray is theta, and minus the tangent of theta is the root. To calculate the tangent of theta, just go 1 unit horizontally and then vertically to meet the ray. Don't forget the sign of these two lines, and the negative sign in front of the tangent. The methods for quadratic and cubic equations can only solve equations with real roots. If there are 3 real roots in a cubic equation, you can find 3 theta angles that all reach the endpoint after bouncing. If there is only one real root, you can only find one. If a quadratic equation has no solution, you won't find any line passing through. Here is an example of a cubic equation: 2x cubed minus 7x squared plus 7x minus 2 equals 0. First, draw the segments. Go right 2 units, up -7 units, left 7 units, and -2 units down at the end. Then draw a line parallel to the second segment, with double the distance of segment A, which is 4 units from the origin now. Do the same for the endpoint. Double the distance from the last segment, which is 4 units now, and draw a horizontal line. Now make a fold so it makes the starting point land on the line from the starting point, and so does the endpoint. The angle theta here is found by drawing a straight line between the starting point and its reflection point over the crease. There will be multiple possible creases if there are multiple real roots of the equation. In this case, we can find 3 folds, which indicates the 3 real roots, 1, a half, and 2. The reason why this works is easy to see. The line connecting two reflection points is perpendicular to the crease, and if you connect all of them, you recover the familiar ray from Lill's method. We can now solve cube root. To make cube root of 3, solve the equation x cubed minus 3 equals 0. Writing it as x cubed plus 0x squared plus 0x minus 3 equals 0 will be better. Draw the coefficients on the graph. Start by 1 unit right, turn up, no move, turn left, no move, and finally turn down and move -3 units, which means go up 3 units. The same folding rules apply. The distance between where the crease intersects the line x equals 1 and the x-axis is the cube root of 3.
Thanks to Pahishan for narrating this video. Without him, this video would be subtitle only, because I got flu, couldn't speak too much. This is my first time to join Summer of Math Exposition. Researching takes way longer than I expected, and my video has a lot of inconsistency because my workflow is kind of messy.